Hey, Rick's people who like to hang out in his closet next to his water heater. Anyway, I'm gonna put this together on my opinions. I'm wrong all the time too, so feel free to kibitz and hammer me or tell me where I'm right or wrong. Here's Rick's feed, which is 3 wires. It's the 2 phases and the ground wire. This is a 2-pole breaker. It's a thermal breaker, so if you over excess the current through there and put too much, and then it thermally will deactivate. Since these two levers are hooked together, if one or the other will pop it and they both go, not just one. You always try, but not always, so you always got to know there's knuckleheads out there who are not going to do it right. But the power is this white wire here coming up, and you always try to feed the power in the top and exit the bottom. And that's what people get used to seeing. You do it the wrong way, and you'll trick people and make it more dangerous for them. You can see that it has the off position is on the bottom as well, so when you pull down, it turns it off. So that's the way it should be. So just guidance that how it should be. But anyway, you can see you got a ground in 2 phases, and then exiting, he's got the ground hooked to here, and 2 phases here that go out to the hot water heater. And that's the way it was before he started this little fiasco. This little thing in the middle, I didn't quite understand that. If it's a way to put more ground lines in, but I'm not familiar with that. And he's got it screwed to the wall. No other extra punch outs or anything in there, so that's nothing too exciting. So let's go to close that one. Let's go to schematic 1. So outside Rick's house, he's got a breaker panel. He's got a neutral bus bar in there. He's got a ground bus bar. And there should be a rod, which he told me is pounded it into the ground, and those are all bonded together. Depending on the salinity of the ground and where you're at and all this kind of good stuff, some of these rods are like 20 feet long, and you only see a few inches sticking up out of the ground. People will play games and try to put a short one in and not a long one because they're trying to save money, making it more dangerous. But you got to watch for that too. I made sure when the guys were doing stuff for my builds, I watched them pound the suckers in the ground till I got confidence in them that they weren't playing games. But so anyway, those wires run over to his box, which is next to his hot water heater. So you got phase 1, phase 2, and a ground line. There is no neutral. No neutral. So it goes through a 30 amp breaker, which are tied together, so it's called a 2-pole. That's the one we had in the picture earlier. So you get 30 amps that flow through. It flows into the load of the hot water heater, and then that gets warm and heats the input of the water, goes in and comes out here, then Rick can take a shower, which is a good thing. Then the return current comes back through this breaker, which is 30 amps. For the 30 amps through that breaker for the second phase. Some people are adding these together thinking, hey, you got 30 amps going this way and I got 30 amps here. Man, that's 60 amp load. The current only flows in a loop. So you can't get 60 here. I don't see the 60. You can't add them together unless you're in parallel. I drew a picture. Later I'll show you to try to help explain that. Then here's the ground in the box that runs to the hot water heater. So if somebody screws up or things go bad, it'll short the ground. Then the electricity finds its way back and doesn't go through you and kill you. So that's the whole trick. It's an easy, they try to make a nice path for a failure mode to get back to the load center. That's the trick. And they're calling this the load center. This electrical box on the outside. Okay, let's try picture 2. Okay, here's what Rick did that we first started looking at. I'm going to point out here, just so you guys know, that when you look at your normal outlet, the hot is the smaller one, and the bigger one is the neutral. The little round thingy, that's the ground. And when you put them in, you should put, it doesn't matter, but you should put the ground on the bottom when you put it in. So, versus flipping the outlet onto the top. And here's my little funky picture of his 2 outlets for his little light. So you can see, I know he's tired of burning up batteries, So he takes one line and runs it into the hot. Then he takes the other one and he runs it over into the neutral. Did I get that right? No, there's a hot, yeah, over here. So it goes into the neutral here. And he had a jumper in there somewhere where he got the ground here. So when the electricity flows off this phase into this one, and then it goes through his little light, be like a little load across here, and it flows back here, it has no phase to get back to like you would have with the 2 poles. So it's on the ground, and it goes all the way back to the ground. So it goes through this ground wire. Could be the copper pipe, who knows, whatever he's got going on in the house. So you don't want ground currents. Zero, none, zero, bad, bad, bad. You want to make sure that that current gets back to a neutral. That's the problem he had. I'm recording. Okay, I got checked on to make sure I wasn't doing something wrong. Anyway, so that goes back to the ground. Trying to remember where I'm at, so I got distracted there. Because you don't want ground currents. I want to get this neutral to the neutral, but there is no neutral out here, so that's what Rick's problem was. That made it an entanglement. That all got into wire colors and all this good stuff, but that's not what the problem was. Okay, here's the example I showed where you got the 2 breakers, you know, the 2 pole. 30 amps flows through the breaker, through the load, and then back out again. There's no 60 there. If you had some kind of jumper here where these are in parallel, where half the current goes through this 30 amp breaker and half goes through the other 30 amp breaker, then I could maybe get 60, but that's not something you're going to see. So, trying to help the person with the, thought it was 60 amps. So this is parallel, series. Another person had it where they were saying that it's a total resistive real load for the hot water heater, which is, you can get them, but those are expensive and it's not common. But you're going to have a resistive real element to a heater or a load. You're going to have a coil, and you're also going to have a capacitance to it. So you're going to have all 3 of these. These are imaginary, and basically will shift your current and voltages, so they're not in phase. And most of you are like, what the hell? Okay, we're not going to go there. I don't think you guys care about that, except for maybe art. Okay, let's go to the next picture. Here was my solution for what Rick has, and trying to, you know, build off of what you got. So he wants to be on the high side of the breaker here, which is good. That way he can have the light on, and when he turns the hot water heater off, by opening the breaker, using it as a switch. So I pulled 2 wires off of there. Here's my load going down here to the front side of this transformer. So I current protected here with a 5 amp double pole breaker. So he's got his 220 or 240 here. So my return path is from phase 1 through the coil, then back around to phase 2. I don't need a neutral. So ain't no neutral. So because you ain't got one. If you had a neutral, we wouldn't be talking about this. So that'll induce a current on the secondary. And if I go 2 to 1 for the ratios, now I got my 120 or my 110. Put a current limiter here for making sure you don't overcurrent. You can also plug in those, a lot of those little bars you guys buy where you plug 15 things in, they got little breakers in there too, so that helps. Those are always a good idea too. So we run it up to the outlet. There's the neutral coming over. I don't ever like having a secondary floating, so you got to reference it. A lot of times I'll do the center tap and reference that. I drew it on the bottom here so it wouldn't get too confusing, and then I'm going to rehook that and reference it to ground over here. The current is not going to flow through here. The current wants to get back to where it came from, so it's going to flow in this loop here. So I've now satisfied by getting him 110 in his outlet and not have a ground current. So no current here will flow. If you have a current here, you're doing something wrong. And that's the one I posted earlier. Let's see where we're at now. What else I got in here? Okay, transformers. That was confusing somebody. I won't mention any names. Rick. Oop, pull it over here. Here's a transformer. You got a winding on one side, the input called the primary and a winding on the second. The number of windings you have here comparatively gives you the ratio, so you can change voltage and current to whatever you want. I can put in 100 volts at 1 amp, and then I can flop it over and have 100 amps at 1 volt, depending on how you wind these things. So I've bought transformers where you'd put in like 240 and say maybe 20-30 amps. In the secondary, you'd put out 2 volts or 5 volts, but you'd be able to have 1,000 amps. These are like big, huge transformers that are freaking 500 pounds or so or more. And you're isolated too with these guys because these are all split and they're laminated together, so you can keep the eddy currents down, more efficiency in you can look up transformers if you get too much into it, but that's basically a freaking transformer. So anyway, I learned about that in the first grade. Okay, what's the next one I got? Okay, there you go. That's one of my favorite catalogs for transformer signal. I wish they found the date in this. Was 1995, so it's 25 years old there. But I like those. I can keep my notes and everything in my manual, so I got it right there when I go to look again, versus on the web where they change the damn thing every 3 days, you know. What do I got here now? Here's some breakers. These are thermal breakers as well. Here's a 3-pole. They're all latched together. Single poles. They all have different ratings to them. Here's a 4-pole going across here. Then the guys will put stickers on them and labels so that they know where it's going for whatever device it's on. This came off of a lower left heater. So there was a machine that had a whole bunch of different heaters on it, and they were running 4 legs over to that heater. So why 4 legs? Well, we'll talk about it right now. Let's see what else we got here. A fuse, different than a breaker. These things pop and you carry them and you replace them, and they make so many different fuses. There's different applications where you want fuses, and there's applications where you want breakers. So we want to get that far, but just know there's difference between them. It's easy to start calling breakers fuses and fuses breakers, and it gets kind of crazy. Here's a transformer that I had sitting in the office here. I thought it would work on Rick's deal, but nope, it was not the right kind. Another picture of it here. You can see the bigger wire on the windings here and the smaller wire on these windings. And then you could hook on for all the different poles you could have, where you could get more selectivity on what voltage you're trying to get out of it. So they tried to build that in to make you buy the transformer versus just one. I'll pop this back up because me and Rick talked about it on the phone the other day. With gold. Gold is not the best conductor. This is a chart that's zeroed out on copper being 100%. You can see silver's the best. Gold is below that, 30% less than aluminum. I was thinking it was aluminum before I went back and re-looked on the chart. But you might think it's always gold, but nope. Silver's better, then copper, then gold, then brass. Brass is down here, then zinc. And stainless steel is down here at 3 to 15%, so it doesn't conduct electricity very well, nor does it do heat that well. It doesn't conduct heat very well. Aluminum is great for conducting heat because you start heating something up on the side, and if your hand's on the other side, you're going to burn the crap out of yourself. Okay, let's go to the next one. Trying to find a pop up, come on. And he wanting to work one. What the hell? Well, there's a different picture. Forgot to close that. Anyway, here's some of this one was made before I even went to work for this company. And this is a vacuum chamber, and there's a cryo pump and water and high voltage and all kinds of good stuff. This slides in here. You'll put lenses or optics in here and deposit thin films on them. This particular machine got shipped out. It was in Scotland, and then it hit a bridge and got knocked off the bridge on the highway, and then it got put into a storage facility for a while. Then he finally shipped it back here, and then it was my project to rebuild this thing. It got about 80% through it, and then they canceled it, so it all went back to the warehouse and sat again. So it kind of sucked. You spend a bunch of effort, you don't get to rebuild it. But this was an old picture that I picked up from somewhere. Okay, now let's try that one. Here was a transformer I found for Rick that he can put on. It's only 50 bucks. I guess free shipping, so he gets a little 46 bucks. 100 watt, that's enough for a light, you know, or plug in his charger or whatever he's doing there. So it's 220 to 110 step down. So here you got here, made in China, nice. 1000 watt rated, can handle both frequencies, but he has 60. The output's, you know, what he needs for the light. It has a cord on the other side, so he can take and cut the cord off and then wire it onto the 2 phases in the ground, because he'll have 3 wires in it when he cuts it off. Then what else we got here? There's a box. Here's Rick's wiring. I love the flag here for the color. But you can see there is no extra wire. I didn't see it. I didn't see there was no neutral in here when the first time I watched that video on video 1 or video 2 or 3 or whatever. I think it was the first one. Till somebody pointed it out, and I was like, damn, that dude knows more. He's smarter than me. Okay, here's that opening up. Here's somebody's meter. You know, he's got Ideal is the manufacturer. That's not a bad one. It's low cost. I didn't say cheap, I said low cost. And ohms is measuring the resistance, and you got different ranges on here. This one's for a diode. I don't know how great this thing is for measuring temperature on here. I don't see the plug on how he's doing that. He should be a thermocouple, but so I don't know what they're doing there for that. I don't tend to. That's extra whistles that won't work, and you probably don't need it. Here they got it set for measuring 9 volts, 1.5. Then you can measure current, and most of the time you're going to measure. Oh, actually that's voltage right there. There's DC current. Then he's got his AC voltage here that he can measure for the ranges, and then DC for the different ranges. So anyway, that's not a bad meter, but I know what you have now, so when we're chatting I can understand where to flip the damn thing for you or help you. Anyway, you guys like, we don't care about Rick's freaking meter. Okay, what else we got? I had something else I was going to put in here. Ames. Actually, this is actually a good site for you guys. Ames Web. They, since I'm not a mechanical guy, even though I try as best I can, if I'm going to press, like I drill a hole and I want to wedge a shaft in there, you got a hole tolerance around one side, and you got the shaft tolerance and the hole tolerance, and you got to size these right so you can get the right fit. So it's not the easiest thing to do, but these boys got these calculators, and you just put the numbers in and you run with it, then you look like you're smart, you know. So they got a bunch of other things too on here, but this is one of my favorite websites, so for the mechanical realm. Let's see, I got Rick's schematic there. We went through that. Here's the transformer. Converts 220 to 120. Where's the picture of the cord? So there's the cord coming off there. So there's the cord. He can cut that sucker off. And it looks like a European plug on there, and that'll plug into the one below over here on it. Oop, I clicked off. This is recording too long already. But you can put the regular American plug on here versus the European plug, but these are way better. The Europeans got us beat on that one. Okay, what else did I have on there? Oh, I was going to show you. I'm going to show you some transformers. So here's a load center where I have, this is a draw off of a design I did. I got 3 phases coming in. They're all 208, so it's a Y. And I got my neutral and my ground. That goes off to the big power load centers where they got lots and lots of power. So I got 150 amp main breaker. I run them in and grab my neutral and my ground, and then I made them jumper over to a different cabinet. So on the bottom of my cabinets, I always have these big, huge copper bars on the bottom, so I can get all of the wires clamped on correctly and not make sure I don't have any currents on my ground, and all of it's on the neutral. So if one of these little wires gets clipped over here on the ground, it don't work. And we had one machine that was headed off to Germany, and up underneath the cabinet where you can't see, one of these little neutral wires, like a 20 gauge or something, got put over on here, and we had like 4 milliamps or something on the ground, and the dude was like, "No, you're screwed. We can't ship it till you fix it." You know, you're like, "Well, how in the hell am I going to find that?" You know, so we dug around and we worked, and we found the wire was off. And once we moved it to the right spot, it was perfect. So I was like, "Damn, I guess I'm good." So anyway, so here I dropped to a disconnect here, a distribution block. So I got 3 of them for each phase: phase 1, phase 2, phase 3. The colors, you guys like colors. Black, red, blue for 208 and 240. And it's brown, orange, yellow if I'm at 480 or 400 volt. Yeah, 400 volt. Yep, that's part of the requirements for sending stuff to different parts of the world. This first one is a breaker, but it's also called a motor starter. And there's extra fuse links in here that you can adjust and set that'll pop. And it'll take the surge of the inrush into a motor. So you tend to put those on a motor versus if you're just running a freaking cryo pump. That's a vacuum pump for you people in Rio Linda. And let's see, I wanted to go down here a little bit. Here I ran a single phase breaker, and I ran it into a transformer in here. So I got my neutral, I got my ground, I got my power. And what I'm trying to do is more of an isolation device, and I'm trying to protect, because it's got arcs and all kinds of crap going on this machine. I'm trying to protect my computer systems in here. All of the, and that says optical monitor too, because that's a real sensitive device for measuring the thin film code rates, and you got to have it perfect. You can't have anything on there. And I branch off and go to a different disconnect for a different panel. But anyway, so there's one I wanted to show you. Okay, here's a transformer. Actually, I should show you this other one first. Try that one. Actually, we'll do this one. I got a plug that goes out there, and I can build these plugs any way I want. So I got 4 big wires, and I got a bunch of little wires. So here's the motor for the roughing pump, and we saw where that came from on the other sheet. And here I got my black, red, blue again. And here's the 3 phases, and there's the ground. No neutral, not needed. The return path is the other phases, so you don't need to have a neutral. So if you guys look at your welders or your electric oven, you got 3 wires, 2 phases, and a ground. You don't have a neutral. The other plugs are I'll run an e-stop through all the different e-stops on the machine, so it's all in series, but I'll also have another little contact block here, so if somebody pushes it, this sends a little signal back to the computer, and the computer knows that, hey, somebody pushed e-stop 1 on the 4 line here, so that's where it was mounted. And they'll have that information, so they don't have to try to go, which one was it that got pushed? And anytime you have a machine and you got 14 e-stops on there, or even 2, they all got to do the exact same thing. Period. That's a very important one. I've seen that broken all the freaking time. But anyway, I digress. Close this, go to the other one. Okay, here's your nice transformer. I'm training Rick up on transformers. This is a Airco design, not mine. I hate this son of a bitch. I've actually tore these apart and almost redid everything on them. Here's 3-phase breaker coming in. I'm going to skip some of this stuff because you guys don't care. So here's a 3-phase transformer. And you got different jumpers here for what voltages you have. And then you got your little bridge for trying to convert DC to it. And here's like another transformer where they're referencing it the secondary here to neutral. TBN is neutral. Then you got the different legs here coming in for remember what they're doing on that. I guess they're just getting 120 here is what they're trying to get. Then so this bad boy converts and goes over here, and it basically runs to this triode, and we're running 10,000 volts. Here's water, goes through it, and the actual, you guys will like this one, 10,000 volts and you're running water. Yeah, water is there. We got these long 15-foot hoses in here, and that's part of the resistive impedance network for this damn thing to work right. And I wanted to show this little transformer here. I'll get back to that water line in a second. Here's another transformer. Oop, I just screwed it up. Sorry about that. I'm trying to go fast. I'm being here too long. But anyway, I run 120 on this side of it. Then on this side of the transformer, it steps it down from 120 to 6 volts. That means I got a lot more current. So I got a lot of current flow here. What that basically does is acts like a heater for this big old triode here. So that's the deal on that one. So here's another transformer in here. Anyway, one of the guys were working on these at once, and they had a little pinhole leak on this water line, and he's standing there measuring and looking, and he had that little pinhole, shot a little bit of water out, hit him right in the forehead, and knocked him on his ass. So he got shocked pretty bad. So you never know what dangers you're going to have on it. Okay, did that one. Okay, so here's another isolation transformer here, running power on this side end. Okay, and this is like 120 if I'm remembering right, and it's just 1-to-1, but the high voltage coming from that CV14 that I just gave you at the 10,000 volts, you'll tie that to it. So I take this whole entire secondary. Remember I say you don't reference the secondary, don't let it float. Well, I'm referencing it to the actual setting of the high voltage supply that you can adjust up and down. They always tied it into the edge. I didn't like that. I always like to tie it to the center of the transformer. So if the guy sets it at 8 kV, I set the center of the transformer at 8, and it also sets the center of the filament at 8. So versus heading it to the side. And these are little tungsten filaments. Does it matter? Probably not, but I always try to keep it the same. So there's another example of a transformer. Did I go through all these? No. Okay, I did that one. No. Okay, I did those. That's done. I'm taking too long. Okay, that's that. I do got the, I was going to show you guys this. I've been putting catalogs and stuff on my spearfishing site there. But on the very bottom, down here, I have the, oop, too far down. Oh, the damn link doesn't work. What the hell? Oh, so I gotta fix that link. Anyway, here's a handbook that's really good for telecommunications, towers, all that kind of stuff. So this is my go-to when I'm working on that kind of stuff. Along with this Motorola manual, which is 2005, but some of this stuff's good. It's just, I mean, they're just baselines. So then I got the NEC manual here, got 2011. I still work off my little hand paper copy here. That's, I think it's 2000. No, it's not even it's like 1995 or something, or 92 that I still use the most, because that's where all my notes are. I got a 2002 here, but I don't use it too much unless I can find the other one. One of my engineer buddies was playing a freaking prank on me, and he sent me this old one, which is 1897 when it first came out. And the changes here compared to the other one are pretty good, so it's interesting. But I was like, cool, you played a prank on me. I got a new post from my site here. Anyway, I got other kind of diving and stuff in here, but you guys don't care about that. Okay, I think that's done there. The transformer. Okay, hopefully that makes sense. You guys got questions, let me know. And we'll see what Rick does tomorrow with the electrician showing up at his house. Okay, later.